Welcome to the FRC 2020 beta event. This is Team 329's presentation. I'm Xing, second year on the team as senior. So let's begin with what our team do in programming. So this is the third year we are doing C++, and we have been doing iterative robot in 2018, and then the time robot in 2019. We'll continue that for 2020. So in this presentation, we'll cover the porting the old robot code to the new library and the differential drive overview, which contains the kinematics, geometry, and doing trajectory. And I also do some autonomous structure with the 2018 robot. It's reusing the structure and not something from the API. And what will not be covered in the presentation, if you heard it will be covered, is the vision that might have been in some announcements, and we will not go into the details of the code because there's not enough time for that. So the purpose of this presentation is to provide an overview of the upcoming new stuff from what we have tested, prepared, and have some ideas for you guys before the kickoff starts. So what we did during beta testing is running our 2019 season robot using the 20 software, testing the new motors for the pre-season project. And we aim to create a West Coast chassis, but the chassis isn't completed yet. And all the projects that I worked on for beta testing can be found in these two repositories. This is my personal repository, and this is the team's repository. And at the end, so beginning with a demo of the 2019 robot code to the 2020 software. And when you open up the robot code, you can, and it will give a pop-up saying it is not compatible with this version, and you to import the project, and you click yes. Or you can go up here and find there's option to import the hello project. And the GitHub repository is public, and I will post the links at the time. So what you want to do is select the Gradle project, and what that means is finding the robot project and select the build Gradle file. And you will be prompted to create the new project folder, which I have prepared before. You do that in folder, and do the import file, and enter the team name. Maggie. So when you import the project, this is basically just copy paste of your files for that. And something you need to do is add your own vendor libraries for this. When I install new libraries, arrow stuff, and so when you pour the 2019 robot code, you might have to change some code. They have, for example, if you have been iterative robot or sample robot, those are removed and then you have to switch to either time robot or command robot. Another thing is that .piniv.h is now deprecated, and I can show you that here. So there's some include stuff error. Open up. Alright. So you can find the .piniv header file like all the way. Anyway, you can see here is a message that if you include this file, so it gives you a warning that it is a bad style and what you use instead. So what that means is that you want to include sort of header files for different classes that you use. So again, this header file is now deprecated. You can see the warning message. So what you want to use is in the header files of different classes like these. Another thing to keep in mind is if you have been using FRC wait methods like us last year, might want to include those in the timer.h files. Another thing is that if you are using command robot, those are now in vendor libraries and they should be automatic process if you use the import project stuff like this append all the commands.json. Because this year they have reworked the command robot stuff. Like you can see here is the new command library, and there will be a more detailed changes coming. So another thing in 2020 is there is a new documentation server. So they move away from screen steps side and move to the docs. So what that means is the new documentation will look like some from Robot Pi or some vendor docs like RE or Limelight. And there is also another more example code with a pretty good organization and a specific advanced programming section. It is a lot better than the previous years. Another thing is that there is a new FRC2 namespace for .piniv J2 package for Java. So there is a timer that uses the unit stub instead of in the double. And the new command-based robot is under this namespace once you use the vendor library for that. Another thing is the PID controller that is a lot simpler to use. So the old PID controller that needs the PID source and the PID output is no longer needed and it's deprecated. So you can construct a controller with only PID value and can get the output by using calculate with the current point and a set point, and then pass the output to set for motors. Another thing is the unit stuff. So this year C++ gets used the unit stuff from another repository, and we'll post the link here. So what this does is units meters on the what this means is like there's a type for dimensions. Once you would declare that by using suffix like underscore s for second and underscore m for meters. And it auto calculates the type of dimension it is. For example, if you times the meters with another meter, it will give you the meter square area. Or divided by second gives you the meter per second. And it is necessary and makes it easier to track the kinematics, odometry, and can. So sometimes you might want to use double instead of units or converting a double to unit. This library does that. So for example, you can convert it to double or any type using second to double or int of note over here. This is the method where you can convert a double to a unit by using type stuff or just the times the double with the unit. And kinematics and odometry, this is something that was already covered in 8190 during the workshop with Java. And I will probably not go over the code, but just an overview of what these are. So in 2020, there will be differential kinematics, odometry, and mechanism and swerve drive as well. So doing swerve is easier than before. And what they do is keeping up the robot's vision and kinematics and do a kinematic in encoders and just try using the kinematics with controller input as the velocity unit, which will represent the chassis speed, and then you would construct the chassis for kinematics, and with these two, it will give you the wheel speed of the left side, right side. The purpose and the purpose of the odometry analysis, it provides the position of the robot in the field. It uses both encoders and gyro. So here in mathematics, usually means the robot heading and some kinematics, so the continuous, but in actual application, it obviously can't be always continuous. So if you use this, it will generate errors over time. So one accurate way of doing this is by using the left position in the right position. These two are important for trajectory. And this is a slide that will be better explained using code, but generally if you are using integrated encoders from NEO or the new CTRE motor for kinematics, so you will have to calculate the velocity to match the wheel velocity generated from kinematics. Here is like the formula for that. And this is the image that sums up the kinematics and odometry for the robot, for the differential robot. So here the E represents the constructed kinematics, and which is the distance between left side and the right side of the wheel, and the velocity, the angular velocity represents the kinematics, which is the chassis speed. The red values are the odometry stuff, which is basically a post 2D. You heard of those from inside 284 stuff. So put this image here because you can see the angle of, in mathematics, the angle of zero is sideways. So you want to, so if your robot starts forward this way, will have to do the X and Y this view, or if you robot front is like this way, you like X and Y this way. So this is something to keep in mind when you read. So the overview for trajectory is setting a config that contains the max velocity and acceleration robot is capable of, and also set the start velocity and the end velocity of the trajectory. And essentially, the trajectory is splines that the robot will follow. And in LPI, they offer the generation of two kinds of splines. And the difference is the waypoints being translation 2D or they post 2D. So this 2 means that whether the waypoint has an angle or not. So you might want a waypoint that is facing this way instead of some automatic angle. And what this essentially does is an equation that will calculate the robot state with the time input. The robot state means the positivity and the velocity of the chassis. The 51 is planning to show an example their presentation. So you can follow the trajectory by these steps. So first you generate a trajectory and you want to start a timer and finding robot state using the timer.get. And once you get the robot state, you put it into a run set controller, which is comparing the current robot position to the supposed robot position. And it will return you a chassis speed to drive using the chassis speed, the kinematics. And once kickoff starts, I find a much more detailed documentation. It was pretty clear. So autonomous. So we never use like commands autonomous. And this is an alternative and probably resource efficient as the commands robot, and this is a timer-based autonomous. So there are three steps in executing a autonomous routine, and the first is initialize the timer and setting the set time here. Then if in condition you would, under the timer you would execute whatever task you wanted to do, and once the task is complete or the timer runs out, you would clear the timer and move on to the next task. And I will try to run the logic after both presentation ends. So the overview, the overall feel to the upcoming season is that the C++ product is the resources that are available for Java. So so my observation on why Java is such a popular language in FRC is it is commonly taught, and the top teams usually use Java because teams like 254 provides a library that is more advanced than WPI what offers. Show you that with two top team examples. So here is 1323, and when you have their GitHub 19, you can see they are using the Team 254 package. that provides those 2D libraries, trajectory library. And another example is in 48, and this is a more interesting example. Let's change this to so, like kinematics and the unit stuff, those are available for Java as well. But they don't necessarily use this library for Java. So let's go back to the example for 48. So when you have their GitHub repository, you can see that they moved from C++ to Java last year, and for a very good reason. And when you look at their drivetrain part for C++, you can see they have method that's a drive velocity, and you can see how many. This repo is for my observation to why Java is more popular than C++. So this method is their C++ code for tweaking. And you can see how many different arguments they have for just one method. And here is another for kinematics C++. As you can see how many different arguments they have for that. And over 100 lines for just kinematic stuff. But in 2019, they had moved to Java to comment to move to Java because they are using the Team 254 library. And once you look at the changes to their drivetrain, you can see how much shorter it is to do like velocity following a path. So like, you don't see a method that is over 100 lines of code. So this is my observation to why teams do that. And while we don't do command-based robots, teams that tested frameworks is reliable and has a lot more useful features. So apparently you don't have to use explicit subclasses and can do commands in a single line of code. And for C++, there's no more need of pointers when you do commands. And generally more flexibility. So this is the end of our presentation. Our beta testing projects can be found here, or the tested projects can be found on here. And I will go over my personal repository here. So this is our import robot project, and this is the other West Coast I have worked on. And generally, this is like the base program of using kinematics, and the version 1 have trajectory, and the version 2 have element. And there's 4 minutes left. Are there any questions? Suppose I can use this time to talk more about the units over here. So essentially, you want to treat the units as double values and use those wherever it can be. And it's a good example because it clarifies what this means by using the definition for them. And it's still implicit conversion, so you can do meters automatic, then it converts to foot, and you divide and auto calculates the values. So the pathfinding program the path that the robot goes to travel on the presets, the field size. I don't know much about the pathfinding program because we have never done trajectory in the previous years. What I see is probably so you have the field trajectories, and you will first set the beginning position of the robot on the trajectory and the end position of the robot trajectory and the points in. So let's say this is 1 meters from x-axis and 1 meters on y-axis. You begin by doing a post 2D of 1 and at the angle. So it's better to show you. So doing trajectories, probably would want to get a header file that contains all the post 2D and translation 2D vectors for that. And you can generate the trajectory or setting the config region. So generally you have set a config of the, and then the types of generating trajectory, then the following trajectory. You can use follow run set. It's pretty simple code, or you can follow the specific state. Like here, the post 2D, you can so the state is a struct that contains the second velocity and the acceleration pulse. You can get those out of structure and then follow that stuff. Now I don't know the accuracy of this, but you should probably use this most of the time. And yeah, this is the end of my presentation, and I will get it to Prateek.
All right, cool. So I'll start with the changes to the FRC documentation. So as he mentioned before, we are now using Read the Docs for documentation. So this is the website that has everything that you need. So I'll provide a link. I'll just type it into the Twitch chat. So I'll get started by talking about some of the new advanced controls stuff. So the first thing that I want to talk about is the new PID controller class. So So WPLib now has a better PID controller than compared to previous years because we completely rewrote the entire program. So 1 second. Anyway, so previously you had to do things like PID source and other things like that, but now all that the PID controller does is that it returns a double. So you can use that double with any motor controller that you want. So let's see, he's figuring out the stream. All right, so I'll just continue with some of the other features as well. So there's a new class called trapezoid profiles. So what that does is essentially it generates a smooth motion profile for one-dimensional mechanisms. So an example here would be, for example, like an elevator. If you want your elevator to go to a certain position, it is preferred that you use a trapezoid profile so that your velocity can slowly ramp up, then cruise for a bit, and then ramp back down. So previously, you could have used something like Motion Magic on a Talon SRX motor controller, but now you can actually use the trapezoid profile class in WPILib. And in addition to this, if you're using the command-based library, what you can do is there's a profiled PID controller subsystem along with the profiled PID command that you can use so that all of the plumbing is automatically done for you. So there's once again a lot of documentation that's available for this already. What I want to spend most of the time on is the end-to-end trajectory tutorial. So this is essentially a step-by-step tutorial for following trajectories. Now, for the time being, this only applies to differential drive robots. So we'll go through this and we'll talk about what we need to do in order to follow a trajectory from scratch. So the first thing that you want to do is actually characterize your robot's drivetrain. So what this means is that it will figure out parameters called feed-forward parameters. So you can actually use these parameters in order to obtain your data. So this is essentially, so if I go over here, there's once again another page for documentation here. And it's essentially a tool that you can use to characterize your robot. So it'll upload some code to your robot, and then you have to enable the robot in autonomous mode, and it will pretty much run the robot back and forth for you. So after you do that, it'll give you a lot of these plots and things like that. And then you will get your feed forward gains, which are visible on the left side of the stream over there. So in the red box. So yep, right there. So you can actually use these parameters. So we'll keep them in mind as we continue this trajectory tracking. What the tool can also do is it can determine your feedback gains. So what that means is that previously you've had to tune your PID controllers. So you start with like a small value and then you start increasing it until you see what works out. So what this tool can actually do is using the characterization that it did, basically using those KS, KV, and KA numbers, it can automatically determine an ideal p-value that you can start with for your PID controller. So you can select your loop type to be velocity. So when we're doing trajectory tracking, we'll be using velocity control. And it will give you an ideal p-value. So in this example, it turns out to be 8.54. So because we're using velocity control, you technically don't need a d. All you need is a p. So with that p-value, you should be able to track your trajectories with accuracy. What you can do after that is we can go to our robot code and start putting in these values. So here you can see a Java example. So we've put in our ks, kv, and ka values as constant. So this is just what the characterization tool gives us. And then you can also see that we have the kp value over here. If we go to C++, you can see that the ks, kv, and ka values are defined with the units library that we talked about earlier. So you can see that that has a value of volts and things like that. If you actually want to learn what these values mean and everything, you can watch my presentation at the P2P workshop, or you can read the documentation on robot characterization, which is also available on the same website. What you want to do next is determine your kinematics. So this essentially helps us convert a linear and angular velocity into speeds for the left and the right side of the drivetrain. So to declare this object, we first need our track width. Track width is essentially the distance between the two wheels on a differential drive road. So usually this is about 27 inches. So in Java, because we don't have a nice unit system, we have to actually declare all of our measurements in meters. But in C++, you can use inches. The example here still uses meters, but you can say, for example, 27 underscore in, and that would also work. And then we can declare a kinematics with the track width. So the kinematics just uses information from the track width in order to convert your linear and angular velocities to left and right. Now, once again, you don't really need to know how the kinematics does this because the step-by-step tutorial will guide you through all the code that you need to write to track a trajectory. The next thing you want to do is actually declare your max velocity and max acceleration for your trajectory. So, for example, in the example here, we're saying the max speed should be 3 meters per second, and that the max acceleration should be 3 meters per second. Once again, if we go to the C++ version, you can see that we're using the units library, so 3 meters per second and then 3 meters per second squared. So that's one of the advantages of the C++ library. And then the final thing is to determine the Ramsey parameters. So Ramsey is actually the type of trajectory controller that WPIlib comes with to track trajectories. So this is better than older things like Pathfinder because it can actually correct for any error that might accumulate. So if a robot hits you, for example, and you go off course, the Ramsey controller will be able to come back onto the trajectory and correct for that. So that's a neat feature. So these are the gains for the Ramsey controller. You technically don't need to declare these variables because the Ramsey controller comes with default gains of 2 and 0.7, but the documentation has not been updated to do that yet. And if we go to the C++, it's pretty much the same. So declaring constant. Once we do that, we actually have to declare our drive subsystem. So this might look like a lot of code, but we'll go through it. I'll go through it in Java because the tutorial went over the C++ a little bit, but all of this should be comparable, and there's a C++ version in the documentation as well. So the first thing that we have is a drive subsystem that extends subsystem base. So all of the new code will be using the new command-based library that will be available in 2020. And then we have our two speed controller groups with two motors on each side, and then a differential drive that basically controls the two motors. So that's pretty standard WPI-lib setup. And then you're declaring your two encoders. Now, all of these examples use the WPI-lib speed controllers and things like that. But if you're using Talons, then you can just replace these members with the Talon SRX motor controller and then the get selected sensor position, which would give you the encoder position for the Talon. You need a gyroscope as well to track trajectories so that you can do heading correction. And then we have our odometry. So we talked about that a little bit earlier, but odometry is basically calculating your field relative position. So as your robot moves forward, it will calculate the robot's position on the field as you move forward or as you turn to the left. So we actually use this robot's position in order to figure out what voltage we need to give to the motors in order to get back onto the trajectory. So if I scroll all the way down over here, we can actually go over individual things that we want to do. So, okay, so the first thing we want to do is actually write an encoder accessor method. So this basically returns the wheel speeds on each side. So for example, if our left side is going at 3 meters per second and our right side is at 4 meters per second, this method will basically return the wheel speed on each side. So we can see we're doing a left encoder.getRate and a right encoder.getRate. We also want to configure the gyroscope. So we've created a new gyroscope. And then we have a method to actually return the head. Okay, so what we're actually doing here is getting the angle, and then we want to bound the angle between negative 180 and 180. We also want to think about how your gyroscope actually returns angles. What this means is that as you turn clockwise, most gyroscopes return positive values. But when we think about math and the unit circle, you want your gyroscope to return positive values as you turn to the left. This usually means putting a negative sign, so that's basically what this code over here does. And that's basically the same code in C++. The next thing you want to do is create an odometry object. As we talked about earlier, odometry is basically calculating the robot's position on the field. So it's the same code in Java and C++. The next thing you want to do is actually periodically update the odometry. So this essentially recalculates the position every 20 milliseconds. So you can see here that we're calling odometry.update, and then we're going to get the current gyroscope heading, and we're going to get the left distance and the right distance. So the odometry basically uses encoder distances to calculate the position. So here your distances, I should mention, should be in meters for Java. And then in C++, you can use any unit. We're using meters by default, but you can use any other unit that you want. The next thing you want to do is actually add a way to return your position. So all you have to do here is create a method to return the robot's position. Finally, you want to create a method that will drive the robot based on voltage. So another thing that we added this year was a set voltage method. So what that does is instead of setting a % on your motor, you can set a voltage. So that will actually compensate for things like your battery voltage sagging and things like that, because we want your voltage to be pretty accurate. And finally, the last thing you want to do is actually create and follow the trajectory. So we can actually, in a file called robot container, we can create a method called getAutonomousCommand. So in here, we can actually create our command. So the first thing we're doing here is creating a voltage constraint. What this does is as you're tracking the trajectory, it will make sure that the voltage given to one motor or the other doesn't exceed a certain amount. What this helps with is that if you're familiar with things like Pathfinder, around sharp turns, your right side or the left side of the robot would go at an incredibly high speed. What this ensures is that your robot will slow down near the curve so that it's easier for the robot to turn and then it can start speeding up again. So that's once again another advantage of the trajectory tracking library in WPILib. What we can do next is create the config for our trajectory. So here we can give it a max speed and a max acceleration for the robot. So as we went over earlier, that was 3 meters and 3 meters per second. And yeah, that is so that taller robots won't tip over. You can, as you reduce the voltage and things like, so when you create your constraint, you can specify the max voltage. So as you lower the voltage, it will slow down more around the curve. So if we think about 2018's cross scale auto, the turns there were really sharp. So this type of constraint would have helped with slowing down so that taller robots wouldn't tip over that sharp turn. So yeah, that's exactly what it's for. Hopefully that answered your question. Anyway, so in our trajectory config, we can have a max speed and max acceleration. And then we can add our kinematics so that once again makes sure that no side of the drivetrain goes faster than the max velocity. And then we can add the voltage constraint that we declared earlier. Now we're going to actually create an example trajectory. So our first waypoint here is 0, 0, facing in the positive x direction. So when your angle is 0, you're facing forward in the plus x. So x is along the long edge of the field. So if your x is increasing, it means that you're going toward the other alliance station. And then we have 2 waypoints in the middle. So we have 1, 1, and then 2, -1. So those are just waypoints. And then our last waypoint is a 3, 0. So this is just one of the ways to generate a trajectory where you have a start and end point where you can specify the angle, and then your middle points where you just specify the x and y, and it will automatically figure out the optimal heading. You can also just give it all pose2D objects, which means that you will specify the heading at all of the waypoints. We recommend using this way because oftentimes you don't actually need to specify the heading. There might be some specific cases where you might want to do it. So we have the option to do. And then finally, you pass in the configuration object. And finally, all we have to do is create the Ramsey command. So this takes in the example trajectory and then a reference to the getPose method that we wrote earlier. So all of those methods that we wrote in the drivetrain will be useful over here. And then we're going to create our Ramsey controller. You don't need these 2 parameters because they'll be defaulted to 2 and 0.7. So this documentation is a little bit outdated now, but we'll update it for kickoff. And then you'll create your feed forward with the values from the robot characterization. And then you have your kinematics object, your wheel speeds, which are just the encoder speeds, your 2 PID controller. So here we're using that P value from the robot characterization tool. And then your tank drive method, which basically takes in 2 values and it will set that in volts. And then your actual robot drivetrain. And finally, all you're going to do is return the Ramsey command. And then once that command has ended, we're just saying, make your robot stop. So that's essentially all you have to do in order to get your robot to do path following. So here, once again, we go through the individual methods that I just went over. So that's essentially it. That's all you need to do. So does anyone have any questions about any of the path following code or any of the other features? I just wanted to mention that I actually helped develop a lot of the kinematics and trajectory tracking code, so I'm really familiar with both the C++ and the Java end. So if you have any questions now or during build season, you can ask me on the NC or the FRC Discord, and I'll be happy to answer your questions. Yeah, so the end-to-end trajectory tutorial is still in a it hasn't been merged into master yet, so that's why it's not public, but it will be by the time we get to kickoff.
Okay. Sorry about the quality of the stream. I said it before, but no, it was to do that. So the presentations from both teams have ended, and you can go anytime you want. But next up is just covering the code and stuff that are already important anyway. So I'm going to cover how to create robot project. So normally in past years you have this template stuff, and you can see how the iterative robot and the sample robot is now doesn't exist over here. You can still create the old command robot, but it is deprecated. So in create a robot like previous years, but in example code, there's a lot more example code that you can look for. Like some of them include like the sword drive or bot. Uh, and generally, the one I want to show you is the differential bot. Here in demo. Also in 2020 there is a new simulation stuff that you can check, but this says that not all vendor libraries support this feature. So, so in this example, so there's this drivetrain package, and it uses their encoder stuff. Right now in beta, there's two issues that you can fix by setting the crashing the internet files a little bit, and this not so. So in this example, you have their drivetrain has a get angle stuff, the units creation, and all of these you can also use the auto keyword for that, and it will auto set the type it is. Here it is about 30 meters per second. But generally, I wouldn't do that just so what type of it. You have a set speed and a drive stuff that you input your controller inputs here. And then the update odometry that will run periodically during the robot. Again, this is the example code that uses the meters unit, and this is like from the center to the left wheel drive train. n times 2 just so that it covers the entire track. Another thing that you can do is like change to auto and change this. Now it is now inches, and sure, it's over here. So normally in this, you can see it construct a kinematics. You will use units meters, but I declare it in inches, but it still compiles because that's the implicit conversion of units. And example code, you can find like some random motor controllers that they put the controller at. And there is a new PID controller that you can declare with only the KP, KD values. So what this drive does is that when you input the velocity and the angular velocity of the robot, you can do the set speed here, which fixing a differential drive wheel speed. And what that does is using the kinematics, the constructed kinematics, the chassis, and then this here method here is converting the chassis speed into wheel speed of the left side and the right side. And this here is the chassis, like the overall chassis. As is a drive station. So here it is the Y state on the left hand of the controller and the rotation. These two are inverted because apparently the Y value is now forward. When you push the Y value on the Xbox controller, it will give you an A value. And here is inverted because on the unit circle, pushing left is a positive angle while negative is negative angle, uh, but on the Xbox controller, when you push left, it gives you a negative value. So you can set so this part is like setting the max speed robot. What that means is how fast the robot can go. So you can like hit 5 here, go max 5 meters per second speed over here. And this is the unit stuff, and you can do like feet per second. 50. And then you can set the angular in radian per second or in degrees per second. And in general, that's how the differential drive using kinematics and the autometry will work. Over here, you would update the autometry with the gyro angle, and then you can do like feet per second, 50. And then you can set the angular in radian per second or in degrees per second. And in general, that's how the differential drive using kinematics and the autometry will work. Over here, you would update the autometry with the gyro angle, and then meters, some sort of units of the encoder distance are used. Over here it is a PID controller. The PID controller. This is the current point, and is a set point generated wheel speeds, and it takes in the double. It takes in double, so you have to convert these units into doubles and these. So something I mentioned in my slide is using integrated encoders. So for neo motors, you probably would use integrated encoders for that. And how you would want to get the velocity is by so this is like the formula to calculate the velocity stuff, and you would put it on here because it's run periodically. Or you can do I believe you can do something like and upper coding and we'll set some conversion factors for that, and whatever value this kind of stuff is, you can calculate using this. I use this because this is like more clear, even yes. So the rest is pretty much the same, and that covers how you do a kinematics drive in C++. I'm just going to create some random projects. Now, sort of cool. So even though we never did any sword, I think and talk about it. So you have the sword modules class, and if you have 4 sword drive modules on your you like for sword module, you construct for sword module in the drive stuff. And the rest is pretty much very similar to differential drive. You have the drive basically X speed, you just speed up your robot and go right into it. And then through kinematics, you will convert to third module states. And generally it goes from that from right when you do that. And so this is just an example code that you can look up to see how the logic of this code works. So if you are using something So here is how like a neo motor sort might work. Together format this. But yeah, this is generally all for the beta testing. Guess I can show you what company it is, what changes. You can see here this applies to all languages. Like some of them are no. Here is the major changes to C++ and Java. Have the command framework, right? And ID control trajectory, factorization, simulation, which we covered most of these in this class. And this is about the end. And if you have something more that you want to learn,